Welcome to another session of circuits and networks. In today's class 5 under magnetic circuits, or we call this one as coupled circuits, we are going to see what is dot convention. Here you can see a typical example where two coils are placed and they are energized by V1 and V2 respectively. V1 is driving current I1 through L1 and V2 is driving I2 through L2, and M is the mutual inductance which is formed between L1 and L2, and these are the dots which are placed opposite to each other with respect to coil 1 and coil 2. For this, how to obtain the time domain circuit and how to obtain the frequency domain circuit and how to frame these equations is what our interest for today's class. So let us go quickly with the session. First, take a coupled circuit whose directions of the currents are given with the input voltage V1 and V2 in these directions, and I1 is flowing from top of the coil to the bottom. Similarly, I2 is also flowing in coil L2 from top to bottom. And the dots here in the coupled circuits are mentioned before the coils in both the cases. So the mutual inductance is formed in these two coils based upon these two dots and the direction of the currents. And how to frame the equation we're going to see here. So let us take this one as case 1 where the direction of the currents and dot conventions are in the same direction. For this, I have to take the time equivalent circuit under figure 1 as B, where you can see this is called as time domain equivalent circuit, where the mutual inductance is formed because of current which is flowing in the opposite coil. For example, I have coil 1 where I have the L1 where the current I1 is flowing, and the mutual inductance is formed in between these two coils because of the current which is flowing in secondary coil. So the mutual inductance depends upon the current which is flowing in the secondary coil. That's why here the dependent voltage is going to become as M di2 by dt. So this is the voltage which is going to be developed as mutually in coil 1. Now in this case, again when you're going to see the secondary circuit, current I2 is flowing in L2, but the mutual inductance which is obtained that depends upon the flow of the current in the primary circuit, and that is why here a voltage is developed, that is dependent voltage source, whose value is M di2 sorry di1 by dt. I hope you understood this time domain equivalent circuit based upon these two directions of the dots and the direction of the currents. Once we are done with time domain equivalent circuit, it is easy for us to obtain frequency domain equivalent circuit. So here you can see in the frequency domain equivalent circuits, only the differential currents are being changed by I1 and I2s, whereas the inductance parameter is taken in terms of reactance. So J omega L1 is the self inductance, and J omega M I2 gives the voltage value whose reactance value is framed with the help of mutually inductance in coil 1 due to the flow of current in coil 2. Same as the case with the secondary circuit. You have self value as j omega L2, whereas mutual value as j omega M I1. So this is how we frame frequency domain circuit from time domain circuit, and time domain is derived as an equivalent for coupled circuit shown in figure A, 1A. So how to frame the equations for total voltage which is going to be supplied in primary circuit will be given as V1 equal to L1 di1 by dt, that is the voltage developed in this coil 1. Also the voltage which is shared due to the flow of current in secondary circuit, so that becomes M di2 by dt. So this becomes the total voltage which is going to be shared in primary of the coil. What will the secondary voltage and the developed voltage when you see from the secondary side? It will be V2 is equal to L di2 by dt, that is the self inductance voltage, plus M di1 by dt, that is the mutually developed voltage because of the flow of the current in the primary of the circuit. So for this figure 1 under A or B or C, The voltage relations and differential current relations are framed in this fashion. I hope you understood how we frame this. Let us go with the case 2 where you have direction of currents are opposite to both dot conventions. For example, when I look into figure 2a, that is a coupled circuit, the direction of the current is from top to bottom. On the left hand side, that secondary circuit also, the direction of the current is from top to bottom, whereas the dots are framed opposite to the coil current conditions. Both are in opposite. In the primary case, we have seen both the dots are placed on the top of the coils. Here the dots are placed on bottom of the coils. So here the mathematical relations holds good, that is plus plus gives the result as plus, minus and minus also results gives as plus. So that holds good over here. So for this also we are going to obtain the time domain equivalent circuit, which will be equivalent to, you can see here, the direction of the current which is flowing in L1 and direction of the current I2 which is flowing in L2, and the mutually developed voltage that is becoming as positive negative from top to bottom, because both the dots are placed opposite to the direction of the currents in this direction. So for the result, we are going to follow here minus and minus of mathematics results in plus. So here also the mutually developed voltage in both the cases will be positive. The same thing follows for frequency domain circuit, and the relation holds good. That is V1 in terms of L1M, V2 in terms of L2M. That is because of the flow of current. The flow of current here treated as differential current, that is di1 by dt with L1 gives one voltage, di2 by dt multiplied with M will give another mutually developed voltage for coil 1, same as case with the coil 2. Okay, let us see an interesting case, that is case 3 and case 4. We'll club them where the direction of the currents and dot conventions are different. For example, in figure 3a, you can see I1 is entering in L1 from top to bottom, and the dot is placed which is also from top to bottom. Whereas in the secondary circuit, I2 is flowing again from top to bottom, but the dot is placed opposite to the convention of the primary circuit. So in this case, we can easily obtain the time domain equivalent circuit in this fashion, where the self-inductance value L1 is positive, so that the positive developed voltage is framed over here, but the current it is flowing opposite to the dot, and that mutual value will be depending upon the flow of current in the secondary circuit, whose convention of the current and the given dot are opposite. So that is why here we are going to get M di2 by dt, that is minus sign. You can check out with the previous two cases, case 1 and case 2. This is different. Same thing follows for secondary of the circuit. Current I2, it is flowing from top to bottom, whereas the dot convention is opposite. So naturally, the directions of these two are opposite to each other, whereas the differential current which is going to be obtained in primary of the circuit, that mutual value is quite opposite to the I2. So therefore, here also we are going to get the mutual value which is quite different to the primary case, that is di1 by dt. Once we are done with time domain equivalent circuit, it is easy for us to obtain the frequency domain equivalent circuit. Mind you, here the condition for mutually developed voltage in both the conditions are one and the same. The same thing follows for figure 4 and of coupled circuit, where you can see the dot convention are quite opposite to this case 3. So for a primary coil and for the secondary coil, the direction of the flow of the currents are different based upon the different dot conventions. So for this circuit also, we are going to get the same time domain equivalent circuit what we have obtained under figure 3b, and similarly we are going to obtain figure 4c, which is familiar to figure 3c, that is frequency domain equivalent circuit. So what is you have to remember is the mathematical notation for these four cases. That is, plus and plus will give the answer as plus, minus and minus will also give the answer as plus, whereas plus and minus will give the result as minus, and minus and plus will also give the result as minus. Based on that, you can easily remember all these notations under time domain and frequency domain for given coupled circuit. So for this coupled circuit under figure 3, V1 will be equivalent to L1 di1 by dt minus M di2 by dt, because the current which is flowing is in the opposite to the flow of the current in the primary. Similarly, V2 will be equivalent to L2 di2 by dt minus M di1 by dt. I hope these equations are clear. Okay, once we solve a few numericals, then you're going to get a complete grip over this topic. So let us do that. Calculate the current I2 of t in the circuit shown below. So here you can see a figure 5 where a coupled circuit is shown like this, where input voltage is V in, which is given as 100 sin t. It is driving current I1, and the coil is having self-inductance value as 0.4 Henry. The mutual inductance value as 0.1 Henry, which is shared between these two coils, and the secondary current, which is flowing in this direction. The torque conventions are opposite. So how to frame the net equations? Before that, what we have to do is we have to frame the time domain circuit. So here you can see I have framed the time domain circuit where I have the input as 100 sin t, current I1 is flowing. So you have L1 that is replaced by 0.4 Henries. You have M mutual inductance value as 0.1, and the currents are in opposite direction. That is why here minus sign and plus sign. The dependent voltage source is in given this direction, and the mutual voltage which is formed, that is because of 0.1 M value, and current which is flowing in this secondary coil which is quite opposite to this. So that is di2 by dt. And similarly, you take this coil of the secondary circuit where you have 0.2 as the L2 value inductance, and mutual inductance value is 0.1, and it depends upon the flow of the current in primary of the circuits. That's why it is minus and plus framed in this direction. So di1 by dt. So once we are done with time domain equivalent circuit, then what it is easy for us to frame the equations, and after that we can find out the value of I2 of t. So applying KVL to loop 1, here I'm treating this one as loop 1. So I'm going to get minus 100 sin t plus 0.4 di1 by dt minus 0.1 di2 by dt equal to 0. So always we are going from higher potential to lower potential, and we are assuming that the voltage over here is negative. So minus 100 sin t, it is taken as a started value, plus 0.4 di1 by dt minus 0.1 di2 by dt equal to 0. Some of you have a habit of taking the conventions in opposite way. For example, the same equation you can replace as 100 sin t minus 0.4 di1 by dt plus 0.1 di2 by dt equal to 0. That also gives you the same result. In fact, this is the perfect answer, that is 100 sin t equal to 0.4 di1 by dt minus 0.1 di2 by dt, and this I'm framing as equation 1. Applying KVL to loop 2 in anti-clockwise direction. So here I am taking this one as secondary circuit, and this is the second loop. So applying KVL in the anti-clockwise direction, I'm going to get 0.2 di2 by dt, that is the self-inductance value, minus 0.1 di1 by dt equal to 0. Since we don't have any voltage source over here, we can easily replace it by 0. In fact, 0.2 di2 by dt equal to 0.1 di by dt. In fact, di1 by dt equal to 2 times of di2 by dt. This I'm treating as equation 2. Now once we are done with equation 1 and equation 2, our interest is to find out I2 of t. So what I'm going to do, I'm going to substitute the equation 2 in equation 1. So I have 0.4 di1 by dt. di1 by dt value is 2 times of di2 by dt. So 2 times of di2 by dt minus 0.1 di2 by dt equal to 100 sin t. So this becomes 0.8, and minus 0.1, it becomes 0.7 di2 by dt. So in fact, di2 by dt equal to 100 divided by 0.7 sin t. which will be roughly equivalent to 142.85 sin t. I hope you understood how we have framed this equation 3. So di2 by dt is obtained as 142.86 sin t. Our interest is to find out I2 of t. For that, I'm going to take integration on both sides of this equation 3. So I'm going to get I2 of t equal to, so 142.86 is a constant value, I'm taking it outside. The variable parameter is sin t. So integration is applied to sin t dt. The limits will be from 0 to t. So when you're going to apply this integration, I'm going to get minus 142.86 cos t. Integration of sin is minus cos. So minus is taken outside. The upper limit value is t, the lower limit value is 0. So I'm going to apply these values. So I'm going to get 142.86 1 minus cos t. In some cases or in competitive exams, they may ask you to find out the value of current I2 of t at t equal to 0. At t equal to 0, cos 0 will be value as 1. So 1 minus 1 will be 0. So I2 of t will be equivalent to 0 amperes. In some cases, they may give you the value of t as 90. When cos t value is given as 90, the I2 of t at t equal to 90 will be obtained as 142.86 amperes. So this is the important thing we should keep in our mind. Based upon the given problem, we have to select the answer, especially in competitive exams. Fine. Let us go with another example. Calculate voltage ratio V2 by V1. It is ratio, not n. N it is distinctly typed over here. Please ignore this n. If current I1 is made equivalent to 0 for the circuit shown in figure 6, you can see we have V1, we have V2, we have two dot conventions. Both the dot conventions are on the top, and 6 ohms, 2 ohms. The resistor values are given. 4j ohms. So it is 4j ohms indicates the reactance, inductive reactance value. 2j ohms also indicates the reactance value, and 2j ohms is the mutual value between these two. So this is also taken as in terms of reactance. So entire thing we can take in terms of reactance values. So I'm going to frame first the frequency domain equivalent circuit like this. You can see if d by dt terms comes, di by dt terms comes, then it is a time domain circuit. And if directly we are going to take I2 in terms of 2j, I1 in terms of 2j, so it is a frequency domain equivalent circuit. In both the cases, we are assuming that the current is flowing from top to bottom, here also from top to bottom. And for this, I'm going to have I1 notation like this, I2 notation like this. This is my assumption. Based upon this, let us frame the equations and finally find out the ratio V2 by V1 by making I1 equivalent to 0. So let's see what we can do. So applying KVL to loop 1 in clockwise direction, I'm going to get 6 plus 4j I1. Why 6 plus 4j I1? 6 is the resistance value, 4j is the inductance value. You have inductive reactance value given by j omega, j xl. So xl value directly we are taking as 4j. That's why 6 plus 4j I1 plus 2j I2. That is the developed voltage over here directly we are taking like this, which is equal to V1. That is minus V1 we have taken on the right hand side. It comes like this. So 6 plus 4j I1 plus 2j I2 equal to V1. This I'm going to treat as equation 1. And applying KVL to loop 2, I'm going to get, see, without framing the equation, let us get this equation in terms of V2, that is 2 plus 2j I2, right, plus 2j I1 equal to V2. I'm applying KVL in anti-clockwise direction. I'm going to get minus V2 plus 2 plus 2j I2 plus 2j I1 equal to 0. In fact, 2 plus 2j I2 plus 2j I1 equal to V2. I hope you understood how I framed this equation. Fine. Now with these two equations of V1 and V2, what we have to do? We have to make current I1 equivalent to 0. If that is done, when current I1 is made equivalent to 0 in this equation of V1, I'm going to get 2j I2 equal to V1 because I1 is made equivalent to 0. So this terminal will go over here. Similarly, when current I1 is made equivalent to 0 in V2, I'm going to get 2 plus 2ji2 equal to V2. Isn't that simple? What is the requirement? Requirement is the ratio V2 by V1. So I am going to take this equation dividing by V1. I'm going to get V2 by V1 equivalent to 2 plus 2ji2 by 2ji2. I2 will get cancelled. So you have 2 plus 2j divided by 2j. With the help of scientific calculator, you're going to get the answer very easily. That is 1 minus j. This answer is in rectangular form. With the help of calculator, convert into the polar form, whose value will be 1.414 at an angle minus 45 degrees. So this is how you obtain the result based upon the requirement, especially in the competitive exams. In the further classes, we are going to see different numericals, and we are going to see the equation framing of currents with inductance values, so that the voltage developed will be obtained in differential equation forms. So that is another part of this particular magnetic circuit concept that we are going to see in the next class. So I hope you like this class. Please share among your friends, subscribe to this channel